Okay, so good evening and welcome to this last talk of this week, week 14, under the online interactive lecture series that the INO project has been organizing now for many weeks. Today we have another interesting talk in this series, which is going to be given by Professor N.K.Mondal. The talk is titled as Development of Particle Detectors for Underground Experiments in India, Then and Now. I know most of the participants here in this today's talk would not, on the meeting would require any introduction about this model, but still it is a pleasure for us, for me particularly, to say a few words before we invite today's speaker. Prof. Mondal made key contributions in the Kolar goldfields, what we call it for KGF for short, Proton decay experiment. It was the first dedicated experiment in the world to test the theory of grand unification of fundamental forces in nature. You will remember this as the GUT series. He was the leader of the TIFR group in the D0 experiment at Proton at Fermilab, US, which discovered the top part way back in 1995. And he was also the technical coordinator of the Outer Hadron Calorimeter project of the CMS detector at Large Hadron Collider at CERN, and then led to Indian group in building the entire HO detector in India. Again, some of you, I'm sure you know, HO stands for Outer Hadron Calorimeter, which is a complete Indian detector from concept to the design, to the commissioning and all that later. So it's a completely an Indian effort. He then led the India-based Neutrino Observatory project, called INO, which incidentally is organizing these series of talks here from the very inception. And till he actually retired from TIFR and went to Saha Institute. He is a fellow of all the three science academies of India and was a J.C. Bose National Fellow. He is also a fellow of the third of the World Academy of Sciences for the Advancement of Science in Developing Countries, FAS for short. He is a recipient of Asher Hoffman Beller Endowment Lecture Award from American Physical Society. He received honorary Doctor of Science degree from University of Burdwan in 2014. Incidentally, that is his alumni institute. As a widely respected member of the global particle physics community, he has been invited to serve on a number of international science committees. He was a member of Program Advisory Committee of the Laser Interferometer Gravitational Wave Observatory, LIGO for short, in US. He also served on the International Committee to review the Keck Accelerator Laboratory, about which I was just talking a while ago, in Japan, and was a member of the International Committee for Future Accelerator Neutrino Panel, IUPAP Astro Particle Physics International Committee, and OECD Astroparticle Physics International Forum. Currently, he is a member of the International Oversight Committee for the Fermilab, very ambitious neutrino project called Dune Project. And right now, he is stationed at Saha Institute of Nuclear Physics, SINP, as an INSA senior scientist. So with this few words about Prof. Mondal, I now request him to start his lecture. Prof. Mondal.
Thank you, Satyanarayana, for your introduction. It was too long, but anyway, so I am going to give actually what Satyanarayana told me to talk about history, not physics. So my talk is basically on history. So, don't ask me any physics questions later. That's not much I'm going to talk about. So the title I have given is the development of particle detectors at TIFR for underground experiments, then and now. Of course, I'll start with then. But before I talk about TIFR effort, actually, if you are going to talk about a history of experimental particle physics in India, you cannot avoid Kolkata. So let me start where it all begins. The cosmic research at Calcutta in colonial India. And this actually was the man who started all this is not as known to the probably Indian community as his contemporaries theoreticians, that is Meghnad Shah and Satyendra Bose. But this gentleman, who is Devendra Mohan Bose, is actually most pioneering work he has done in the experimental particle physics in India. So actually, let me just give you just a short history of what he has done. He has done his MA in physics from Presidency College, 1906. So you can see that he is several years ahead of S.N. Bose and Meghnad Shah duo. But so in 2006, after he completed his physics in MA in Calcutta, in Presidency College, he then moved to Christ College, Cambridge, and he was there from 1907 to 1913, and worked with the J.J. Thomson as well as C.T.R. Wilson, the two pioneers, right? I mean, J.J. Thomson for the discovery of electron, and C.T.R. Wilson was the inventor of the cloud chamber. So these two pioneers, he worked there at Cambridge, and then he moved to Calcutta back. And in 1914, Ashutosh Mukherjee again took him under his umbrella and made him the Rasbihari Ghosh Professor of Calcutta University. But shortly afterwards, he got a travel scholarship to go to Germany. And he went to Germany for a short time. However, the First World War started, and he got stuck there. And that was really great thing to happen, because he actually there worked with many pioneers, and especially cosmic ray pioneers, Eric Wegener, who did this, intensity measurement as a function of height and so on. And he worked on various, cloud chamber related work, nuclear disintegration by cosmic rays and so on. He came back, and of course he became Pali professor, and then of course he continues his professorship of Rasbihari Ghosh Professor at Calcutta till 1934. And 1934, when C.V. Raman moved to IISc Bangalore as a director, and this Palit professorship was vacant, and he was made the Palit professor from 1934 and 1937. And 1937, after J.C. Bose, he was made the director of the Bose Institute, and then he retired from there in 1967. Actually, you don't probably, I didn't mention so far, he was the nephew of the Jagadish Chandra Bose. The Devendra Mohan Bose was the nephew of Jagadish Chandra Bose. But what he did actually, this is his, what he did great work in both nuclear emulsion and cloud chamber, but using and created a great, many physicists of high standard. And one of them is Bibha Chaudhuri, and Bibha Chaudhuri was T.M. Bose student, and together they actually exposed this nuclear emulsion in the mountain altitude in Sandakpur near Darjeeling, and almost discovered the pi meson. And apart from that, this thing that what you talk about, all the people talk about pi meson discovery, what they have done, they have basically introduced this technique of using the nuclear scattering in emulsion and the grain density, use that to measure the mass of the particle that for which the track is there finding. So they use these two techniques, and these two techniques were later used by Cecil Powell and his group and then found the pi mesons ultimately. So this was a great time actually it was happening, and they just missed that because just during the war, when Bibha Chaudhuri was doing her experiment in 1939, 1940, and when the Second World War started, and he couldn't get the high quality of this emulsion that they needed for their experiment. And that is why they actually stuck there, and they had to use this old technique. But they have done great work. And then these other three gentlemen, S.K. Ghosh, R.L. Sengupta, and Mriganko Sinha, they became expert in cloud chamber. Of course, later all of them went to the Blackett's lab in Manchester to work with there, all four of them. But the specialty of R.L. Sengupta and M.S. Sinha was in the cloud chamber. And you may raise that question that why I am talking about them so much here, because you will see in my next slide, there is a direct link of the experimental activities that took place in TIFR a little later after these people are doing their work at Calcutta. So now let me go to the Bangalore side, Cosmic Ray Research Unit at Bangalore, and where Homi Bhabha has already arrived. And he was desperate to have some experimental data because of the war, he was not having access to data. So though he was a great theoretical physicist, he made himself to become an experimentalist. And so really the seed of experimental high energy physics research of TIFR was sown even before TIFR came into existence on the 1st of June of 1945. In 1944, Homi Bhabha took the initiative and he flew 2 telescopes with GM counters built at IISc, sandwiched with lead plates using US airplanes at that time stationed at Bangalore during the war. And that was the first measurement of high altitude measured intensities at equatorial latitude that was done. But then he wanted to build a big experimental group and he wanted to build an instrument. So next he attempted to make cloud chamber. But who will make the cloud chamber for him? And that was the cloud chamber. He invited Mriganko Sinha from Kolkata, who was student of D.M. Bose. And Mriganko Sinha came to Bangalore and built a 12-inch circular cloud chamber similar to the one available that time at Blackett's lab at UK. And this 12-inch cloud chamber was really the first instrument that TIFR experimental group acquired for studying the cosmic ray studies and so on. And when Bhabha moved little later from Bangalore to Bombay, this is the cloud chamber they carried from Bangalore to Bombay and started doing experiments. So this is really, you can see that these students that created by D.M. Bose was the pioneer and they built the first instrument for TIFR. By the way, I didn't mention both R.L. Sengupta and Mriganko Sinha was my teacher at Burdwan University. But I didn't know that time the great work they have done actually. Much later, Professor Srikantan told me this story actually. Okay, so now let's go back to the early particle physics experiment at TIFR. So the experimental activities at TIFR was centered around 3 different techniques. One was the cloud chamber and the 12-inch cloud chamber that was built. Other one, the GM counter. And that time, in TIFR workshop, they are making the Gargamuller counter using glass tubes. And so glass blowing section actually started to make those GM counters at TIFR. And I will show you later that this same glass blowing section helped much later to make the neon flash tube, which was used for the many experiments at KGF underground site. So now this is the GM counter and of course the emulsion. These are the 3 areas where they concentrated their experimental activities around them, and various groups were built around these activities, around these experimental activities. Now move back to this one, and what really I would say the starting point, Rajaji is here, so he knows much better than me. The starting point of the experimental particle physics activities or even particle physics activities in TIFR was actually this conference that happens in Bombay in 1950. And Homi Bhabha organized. And many physicists came from abroad. One man was invited specially to come there, and he was Bernard Peters. Bernard Peters was involved, as you know, in the Manhattan Project, and he was hounded by the McCarthy Commission in US, and he was probably losing his job in Rochester, and he had to move out of the country. It was that bad. So Homi Bhabha invited him to come to TIFR and as a visiting professor. And it was good that Bernard Peters accepted that offer, and he came to TIFR. And during the 50s, he built up a big group of pioneers in cosmic ray research in TIFR. And these are actually, recently when I wrote this biography of Professor Menon, myself and Sidhu gave this title of these 9 people as Navaratna in Bhabha's this thing. So here, these are the people who started all these experimental activities. Homi Bhabha himself, Bernard Peters, Bibha Chaudhary that time came back from Blackett's lab in UK, and was in TIFR for almost 8-9 years, and before he moved to PRL. Roy Daniel, he was also in Bristol along with N.K. Menon, and came back from there on an expert in emulsion that time. Sukumar Biswas, Professor Sikantan, he was a homemade product, came from Bangalore. Homi Bhabha interviewed him and took him under his umbrella. And Yaspal, Devendra Lal, and N.K.Mondal, of course, came from UK and from Bristol and joined this activity. So these are the people who started the overall cosmic ray research activities in TIFR and did wonderful job during the 60s and during 50s and early 60s, each of them in their own field. Now, here is a much later picture of some of the pioneers. It is Bernard Pater, Professor Sikantan, Devendra Lal, and Yaspal having tea. But let me just come to KGF. The KGF activities really started in 1951. And the story was given to me by Professor Sikantan to tell that Homi Bhabha called him one day. He said to that Sikantan, you have to go to Polar Goldfield. You go there because by that time, Professor Sikantan has become an expert in instrumentation because he built actually after the war. He just went to the Chor Bazaar in Bombay and got all this electronics from there and built the muon lifetime measurement experiment at TIFR. And using his setup, he measured the muon lifetime. And that was his expertise. And so he was told that you make an instrument and go to KGF and measure the intensity of this new particle muon, which is also known as heavy lepton, and study its properties. How much it is similar to electron and what is its property. And that was, he was sent there to KGF. And so this is the KGF. This is I'm showing the lab where many of us spend our large fraction of our life, but that's not the place where Sikantan started his experiment. He was in a nearby SAP called Nandidug mines, and that's where he started his experiment. Okay, so now let me talk about those pioneers who are there. Not all these are pictures. This is a picture of all of us, and there is not all pioneers. The pioneers are here in this picture. The Professor P.V. Sikantan, who started this experiment at KGF, and he was shortly joined by two other persons, Professor S. Narayanan and Professor Ramanamurthy. And these three started actually Sikantan came, and within a short time, Professor Narayanan came, and Professor Ramanamurthy came a little later, and they started this work at KGF actually. So I call them the pioneers. Now, what they did at that time, and at KGF in 1951 to 1954, using a GM counter array, because I have already shown you that TIFR workshop were making those GM counters in large number. So made a horoscope of GM counters of 4 layers, and in between they had these absorber plates and this was all connected to the cathode follower, and then they are taking the picture. Actually, they're putting in a horoscope that this was mapped into a light emitting instrument, and then basically a bulb. And whenever the particles this will go through, the bulbs will glow and they will make a track. Okay, what they are doing, and there is a camera which is taking that picture, and so on. So this is a very simple experiment, and they went not too much depth. They only went up to 900 feet. Okay, using this instrument. That is actually, if you convert into muon energy, will be 200 GeV muon. But that was a great energy at that time to go to. So they went up to great energy and measure the intensity of the cosmic rays and over this area. And you can see that, and then they get this what is the absorption curve and so on, how the muon intensity is falling down, and was doing a great work that time. But then it was around 1954, the mining authority told them, you please wind up your experiment and go back to Bombay because we are going to close down the mine. So they had no option because they are about to start the cloud chamber measurement at KGF. Okay, they want to start the cloud chamber measurement after this GM counter measurement. They want to start. In fact, they started the cloud chamber experiment, but they had to wind up. And they came back from there because there is no place. So they moved to Khandala tunnel, and for the next several years, they are doing this cloud chamber measurement in the Khandala tunnel. But that's a different story. I'm not going to talk about that. So this is actually, so then this is the cloud chamber. This is not the cloud chamber that was used at KGF, but I'm showing you a cloud chamber that we had in an exhibition we kept there at the TIFR. So the underground experiment at KGF, however, came to an abrupt halt, as I told you, in 1954, and they're asked to go. So we thought that is the end of everything, that we lost the KGF forever. But that's not what happened. Of course, Sikantan went to MIT, and then he came back, and then he found that the KGF got a new lease of life. The KGF mine got a new lease of life as the management of this mine was taken over from the private player, first by the government of Mysore in 1956, and they called it Kolar Gold Mines Undertaking, and then finally by the government of India and renamed this Bharat Gold Mines Limited, BML, as a public sector undertaking. So once they are back and it is under government hand, you can go back and start the experiment in there. So the next phase of experiment started little later, around 1960, and 60 to 63 is the next set of experiment. And they continued actually this set of experiment. Sorry, I missed some slide here. My God, I mixed a slide here.
Do you have them?
No. Okay, then don't worry. So the experiment that I had the picture of the people. By that time, 1960, they started. There are others who have joined that experiment. Okay, and by that time, Professor M.G.K. Menon is already getting involved in the underground experiment at KGF, and V.S. Narasimham also joined as a student that time, and fresh from the training school, and then came Professor Miyake as a visiting member of the TIFR team from Osaka City University, and a good friend of Menon. So they are also there, and they built up a bigger group, and they decided to map this muon intensity, what Sikantan has left, and take it down to as deep as possible, and map the cosmic ray muon intensity as a function of depth. And that was really a pioneering work that they have done. They have gone in these 3 years up to a depth of 2.7 kilometers. Okay, that means up to that, if you convert into the grammage, it will be 8,400 meter water equivalent. That means if you take it in the ocean, they have gone up to 8.4 kilometers. Okay, so that depth. Okay, that is the amount of matter they have gone to. And the instrument they have used is same GM counter, but this time sandwich the GM counter layer with scintillators on top and bottom. So you have scintillator layers. Here you can see this conical structure in top and bottom are the scintillator. At this cone is actually top, and bottom that is the proportion. Photomultiplier tube, and in the middle there is the Geiger-Müller counter. And they had something like one such instrument for the shallower depth where the muon intensity was still reasonably high. But when you went to deeper level, they had to put two of them side by side to get enough statistics. And they are doing that experiment as a function of depth, as I told you. And finally, around that, the depth is maximum depth of 2.7 kilometers. And he started this experiment at 2.7 kilometers, and they're waiting there, but couldn't find any new count actually. And then that time the people got bored, and they all came back. Physicists all came back to Bombay and left a postcard and with the address written of the TIFR address, and given it to the local technician who was looking after this apparatus, and tell him if you see the count, you post this letter. Otherwise, just watch this instrument. And up to 3 months they waited, and the postcard never came to them. And that non-arrival of the postcard, they celebrated, because they ultimately found a place where no cosmic ray muon has reached in 3 months' time. Then what is the importance of that one? That importance of that one was actually proposed by Menon, Ramanamurthy, Srikantan, and Miyake in a paper in Novocimento in 1963. And what they said there this is the ideal place for carrying out experiment to study cosmic neutrinos. Cosmic neutrinos are already in the horizon, and people have measured already their flux and so on. I'll come within after a few slides. They can do that type of experiment. They can set up experiment to put lower limits on the photon lifetime, and because that time the estimated photon lifetime was 10 to the power 26 years only. Okay, so they can go much, they do better. And of course, they prove the existence of intermediate vector boson, the predicted mediator of weak nuclear force. This paper actually started the ball rolling for a series of important experiments to be conducted at KGF over the next 30 years to study neutrinos and also to explore ideas of baryon non-conservation there. In fact, this paper, you can see that the result, that the depth intensity curve came on a later paper in 1964. This is the famous MNR paper, Miyake Narasimhan and Ramanamurthy paper, where they gave that complete depth intensity curve. But this proposal that this site can be used for neutrino experiment has came 1 year earlier actually, because the importance and the competition that was already taking place in atmospheric neutrino studies. Because the team of Frederick Reines is already planning to do similar experiment, and they didn't want to lose the time, and so they starting the experiment there. By the way, I think the people like Rajaji knows that Fred Reines came to KGF to do the experiment first before he went to South Africa, but he wanted to have the mines, not to have the collaboration with TIFR, and Baba will not take it, and so is there nothing to it. In fact, that is why he pushed Menon and Srikantan actually more further that go ahead with all resources and start the experiment. And that's what the experiment was started. But Miyake-san was already there, so Osaka City University became a part, and that time Arnold Wolfendel, another friend of Menon, came from Durham University, UK, and he joined this effort. So it became a big international collaboration, Tata, Durham, Osaka neutrino experiment, UK, India, Japan collaboration, and they started the experiment. So they had to plan the experiment, but the basic input they needed for planning and designing and finalizing optimization of the experiment is already in hand there. Because it was already known that the high energy cosmic ray particles interact in the Earth's atmosphere and produce pions and kaons. These pions and kaons decay and put into muons and neutrinos. It was already there. Already the Jetsapin and Kuzmin from Soviet Union have made careful calculation of the flux and angular distribution of these neutrinos. So that was available. Already the experiment of the muon neutrinos has been discovered at BNL, and they have already measured that they have already shown that the muon neutrinos is a separate species than the electron neutrino, and already measured their cross section in this energy range, and which is supposed to be around 10 to the power minus 38 centimeters. So all these inputs then allowed the KGF group to estimate the expected rate of neutrino interaction underground and to optimize the size and type of detector they will need to detect it. So they choose the tunnel at a depth of 2.3 kilometers at the Hitchcock shaft in the Champion Reef mine, and as the site for the experiment. And what they set up in next few years there? They set up actually not one, but 7 neutrino telescopes next to each other. Each have different capabilities and different purpose. Okay, there are so the 7 telescopes actually can be categorized into 3 types. There is called the telescope 1 and telescope 2. They are simply you have this neon flash tube. You can see these trays, 3 trays in the middle, and with a 2 LED blocks in between, and these are the neon flash tube. And then on the side there are those scintillator cones that you can see, and for trigger. And whenever there is a charged particle like muon will go through that, the scintillators will produce fast signal, and that will be used to trigger the high voltage for the neon flash tube. And neon flash tube, by that time, and the particle has also gone through the neon flash tube, ionizing the gas inside at low pressure. And then what will happen is that this trigger from the scintillator will make the high voltage and also the camera on. So the neon flash tube through which the particle has gone through, they will flash, they will give light, and the camera in front will take the picture. Okay, that was the experiment they're doing. It's simple, there is no magnet or anything. And this also, there was only projected geometry, it has only projected zenith angle it can give you. This telescope 1 and 2 will not give you the real space angle, that is azimuth and theta. It will give you only theta. Then there was the spectrum graph 1 and 2. There has a magnet in the middle. Okay, they had a magnet in the middle. The magnet will help you to measure the momentum of the neon. So this was there, and you can see all around. So there are all around surrounded by the tracking chamber, that is the neon flash tube, and then in the middle there is the magnet. So they will measure the momentum. And finally, the telescope 4 and 5, they had both actually, they have a stereo telescope and stereo thing that so that they can measure the real space angle of the detector. Okay, so that is how they have set up of different experiments. Of course, they came in stages. They didn't come in together. So they came. So telescope 1 and 2 became operational in the early 1965, 3, 4, 5 by March 1966, and 6 and 7 in 1967. And the first neutrino event was detected in early 65 in the telescope 1 after it became operational. And this was published in Physics Letter on 15th August 1965. 2 weeks later, Fred Reinecke reported their observation in the Physical Review Letter. So KGF team beat them by only a very narrow margin of 2 weeks. Okay, so this is actually, I should give the credit to both of them because probably they are observing in the same time. Only within 15 days the both paper came. But anyway, in historical perspective, these 2 experiments are a great, pioneering experiment because they started the ball rolling for many other experiments later. So now this is actually the paper that was first published in the Physics Letters of 15th of August, and using this experiment, and this is the, you can see that this is clear. So at that depth of 2.7 meters, you are seeing horizontal neon. So if you imagine how much matter it has to go through, if it is produced by the cosmic rays in the Earth's atmosphere, this is not possible. So this is why they are locally produced neon by the neutrino interaction in the rock surround the detector. Okay, so that is how they detected this one. And then of course they had this in this from the scintillator, they could also find the timing. You have the scintillator layers on both sides of the tracking chamber. So from the timing of the scintillator, they can also know the up-down direction. Okay, they are taking the timing in oscilloscope. The oscilloscope pulse, they are taking the photograph of that. And from there, they could say whether it is upward going or downward going neon. And that is also help them in finding their number. So ultimately, so the importance of the KGF neutrino experiment, apart from discovering that, yes, the atmospheric neutrinos are there, and the study of neutrinos underground became an important area of research in the field of particle physics around the world later. And several Nobel Prize winning discoveries were made using neutrinos underground, as we all know. And all started at Kolar Goldfield in India. Now, let me just talk about other things. This is not the only thing you think of, that they have only studied atmospheric neutrinos. They even use those neutrinos to look for, actually, this is also, I'll call it the beginning of neutrino astronomy. Because those neutrinos, once you have identified, you can point them back in the sky and find out which direction they are coming. And that exactly the KGF team did. And this is actually the projected point in the sky of the origin of the direction of those neutrinos. And here you will see some of them has a long line because, as I told you, if you remember, some of those detectors didn't have the solid and space angle measurement, only zenith angle measurement. So you can only project them over a certain part of the sky. But some detector has good spatial angular resolution, and those are shown in point actually in the sky. Okay, so of course they didn't see any statistical excess event, but again see that one. This became really one of the earliest neutrino astronomy experiments that was done, and today this is really the most exciting field in South Pole, and a lot of new things are going to happen in this area. But all these ideas also there in the 60s at Kolar Goldfield. Of course, this is not the neutrinos only. They have seen other puzzling events, and then for this event, Rajaji came into the newspaper, and this is the polar event, and this was interpreted by Rajaji and KVL Sharma as a different, as a decay of a new kind of particle, and after that, even Glasso wrote paper on that, and they found this event is that if you see those detector events, they saw 2 or 3 tracks. And if you extrapolate the track, they meet mostly in the air, not in the rock. And you can imagine that the number is such that here, if the neutrino comes and interacts in the air, that probability is extremely small. So, but on the other hand, if something happens in the rock and produced a new particle, and the particle comes out and decays and produce these particles, and this, of course, they calculated within this hypothesis the masses of these particles and the lifetime, and they turn out to be around 2 GeV and at 10 to the power of course, nanosecond timing lifetime particles. I have shown some few pictures, but there are some more pictures of the kind that they published from this experiment, and which also we saw later in the proton decay experiment, some examples of that. Of course, this looked, that was exciting time, and certainly all the accelerator laboratory at CERN as well as Fermilab, they looked for polar event in their detector and then didn't find any of them. However, still there is no explanation given even today for this event, and of course Rajaji and Murthy much later and very recently they have given a new interpretation of this event in terms of dark matter decay, and so this is still alive and probably will be explained in some future experiment that we will do in this area. Okay. Now, next experiment that I want to talk about in KGF is called the second theta effect. Many of you are probably talk much about the KGF neutrino experiment, but didn't know about the second theta experiment. What is the second theta? So let me first briefly explain what is the second theta method. See, now you have seen that the the muon you measure underground. These I'm talking about the muon, not neutrino. Underground are decay product of pions and kaons in the Earth atmosphere. Now, the pions and kaons are produced, and after they are produced, when they move some distance, they will do 2 things. One, they can interact or they can decay. And whether they will decay or interact will depend upon the density, local density of matter at that point in the atmosphere. And if you see in the picture, if a pion is coming in the vertical direction, the zenith angle 0, let us say, then it will reach certain distance where the density will be much higher. Then for the same distance, a particle moves, let us say x gram per centimeter square, both this track which is coming vertically and in the angle theta is going. So they will travel in a certain matter, but when they reach the point, they will see lower density. If the particle is coming in a large zenith angle, then the local density will be much lower. That means at that point, the probability of its decay will be much higher than its interaction. So if you go underground and just take the angular distribution and take the same amount of matter, then even if the underground, they have gone through certain amount of matter, x grams, let us say, you will see more number of muons if you see in the large angular direction than in the vertical direction. Okay, for the same distance. So this was that means the number of muons will goes on increase as a function of sec theta, basically. Okay, so in the vertical direction, if it is x, in number is n, then in the at angle theta, their number will be n sec theta for the same matter going through this one. And since they are measuring this angular distribution of muon, and they could do this experiment. Okay. Now, what is important? So what? You are measuring this. Why it is important? Because if it's the second theta effect they can see, that means the pions and kaons are the source of this muon. However, if there is a deviation from that second theta effect, then there is some other source of muons coming from the atmosphere. Maybe direct production in the primary interaction. If there is a direct production of muon, okay, I mean, later on, of course, those direct production exist, because of the charm decay, because charm lifetime is so small, it doesn't matter. Of course, that time charm was not there. Now what happens is that time that a strong group in Utah, who was also doing neutrino experiment a little later, they published this paper, evidence for a new production process around 10 to the power 12 electron volt muon, not from pion and kaon, because they didn't see the second theta effect. So they said that muons are mostly produced direct production. And that was a fantastic result that time, because there is a new cross section, new interaction is happening in the atmosphere and this one. So they published their PRL paper around that time, and then KGF group didn't agree to that one because they already knew the angular distribution. So they did dedicated experiment very quickly and measured this second theta effect in a very high accuracy and showed that this direct production doesn't exist. And later on, the Koeffel group had to withdraw their papers actually. Or when they said yes, there was a mistake in this measurement, and this is not the right result. So this was really a very good result that came from KGF after this neutrino experiment. Okay, so this was going on the experiment, and when I joined KGF in 1977, and that was the famous statement, and this is anti-007 statement by Sally Glasso. He made this statement around that time: the diamonds are not forever. Well, what is the implications of that? What he meant actually, that he has this grand unified theory, which to unify these three forces, and if that happens, the proton will decay, and of course, if proton decays, diamond will not remain diamond, and that was his light way of saying that a proton is going to decay. And why the proton will decay? Because that time, after this, success of the electroweak unification, the next frontier to attack by the theorists was to combine all these three strong, weak, and electromagnetic forces, as they are of similar nature theoretically. They're all gauge forces and so on. So they will be combining, and of course that the coupling constant is running and running in opposite direction. Strong coupling is getting weaker at the higher energies, and so at that time they estimated that at 10 to the power 16 they will unify, and that means this unification is basically to put this quark and leptons into the same multiplet, okay, into the same family. That was the idea, and this came. And if that happened, what will happen is a new set of intermediate vector boson will be there, and they will exchange particles, and they will convert a quark into an electron or a positron, and the proton will decay. Okay, that was the idea. And they also came up with a lifetime of proton is 10 to the power 30, 10 to the power 30, 31 for the lifetime. And by that time, the reach or the lifetime of the proton from this neutrino experiment at KGF and Rhines and so on is around 10 to the power 29. So that means another order, you will be seeing those decay actually of proton. And then you can roughly calculate, if you have need 10 to the power 30 or 10 to the power 31 is the lifetime, you need something like a 100-ton detector to get a handful of events at 1 GeV. You don't have to do any fancy work. You will see this peak easily at 1 GeV. Okay, that is the mass of the proton, if you look into this event. And that was really very, very exciting proposition. And we could do that. India can do that. And that is the time when, and of course, and all this time, the Glasso and Jogeshpati, Abdul Salam and Jogeshpati also has the similar theory. And Salam and Menon was good friends, and there also Salam was trying to also convince Menon that India should go for this experiment at KGF. And then all put together, and then there was this cosmic ray conference was happening in 1978 at Tokyo, and there all met, and then came back and told us that we have to do proton decay experiment. I was actually by that time halfway with my detector to measure the multiple muons and get my thesis. Actually, that means I have built already 300 proportional counter in 3 layers and 6 layers, and I was measuring multiple muons at a depth at 30-second level. But I was told that stop that experiment. Imagine a graduate student was asked to stop his experiment halfway when he has just spent last 1 year and built that detector. He said, forget it, this detector, we have to make now 1600 proportional counter, because that is the number of counters you need to make a 100-ton detector. Okay. Well, your bosses ask you, you have to do it. And so this is actually that time 2 types of detector was planned to do proton decay. One is the tracking detector and other one is the homogeneous water Cherenkov detector. We actually went for the tracking detector because we have already, as I told you, I was making proportional counter for my thesis experiment, and the US group, there are 2 groups, okay, IMB and HPW. They actually, this is IMB is basically Reines and others, and HPW is Deb Klein and Carlo Rubia. They are planning to use water Cherenkov technique and put photomultipliers and look for, because the main photon decay was this, decay into positron and pi 0, and positron and pi 0 will produce back-to-back electromagnetic shower, and they'll be able to see nicely in the Cherenkov light coming from there. And we wanted to do the other way, the tracking calorimeter, because that's where the expertise lies. This detector, this water Cherenkov, they could make much bigger. Their detector size was roughly around a kiloton, okay, and ours was only 100 ton. Because we are looking for 10 to the power, we are hitting for 10 to the power 30. We are told the lifetime of proton will be 10 to the power 30 or 31. So we knew that if that is so, we do our detector. Well, those started the major, instrumentation work at polar gold field itself. We can't make those, we have to make those detector in situ, and started making those proportional counter. They are these long proportional counter you can see, and at KGF, and each of them is 6 meter. Actually, in the first experiment, we had both 6 meter and 4 meter counters, and with a central wire is a 10 centimeter by 10 centimeter iron tube, and we had a tungsten wire 100 micron thick at the middle, and we filled this with an argon carbon dioxide at 90 20 90 10 ratio, and started. So this is actually started our mini factory of making the counters. Then here are some physicists, M.R. Krishnaswamy and B.S. Narasimhan. They are looking into this, characterizing those counters, how good they are. Swamy is looking into the amplifier pulses in the scope, and Narasimhan is looking into the, the spectrum coming out in another detector here. Okay, multi-channel analyzer here. Okay, so they are doing that testing, and then you have to do this methodically, all these 1600 counters. And then, of course, you need 1600 channel of electronics. But who will build them? You are not going to anywhere, not Bangalore, not any factory. You have to do yourself, no expertise that time. How to get? Who will make those? We didn't have actually, we have only one or two technicians only working with us. So we got this idea, so okay, let's go to the local college and just motivate them and bring them, train them, and make this amplifier, 1600 amplifier, test them and so on. And that is how we started our cottage industry of making those counters and electronics and so on. And slowly, by counter, we started making our stack of proportional counter. They are orthogonal, X and Y proportional counter in between 6 millimeter thick iron plate, and goes on building this detector. There was total 32 layers in this first detector that we built, and once it is built, it looks beautiful. So whole detector here is 32 layers. It's looking into that, but here actually behind that detector is our control room, electronics control room, what it look like. And this control room has all these cable, 1600 cable coming there, and then going to amplifiers are there close to the proportional counter, but discriminating them, converting to digital pulses, record them, everything are done in this experiment. There are no computer. Ultimately, there is a paper puncher actually, a paper tape puncher, and that will make holes into the paper tape because so many dust there, no computer. Anyway, that computer came much little later, and that's how the experiment started. Once it started, we started getting also very important visitors coming to us actually. And many, actually, I was busy actually, and not for doing experiments sometime, to taking the visitors underground actually. And here 2 important visitors you can see, Abdul Salam, and came to see whether protons are decaying or not. And in the bottom here is Nambu, came from Chicago to visit our lab. Spenta brought him there. Spenta is also there, and so on. So this experiment actually came into existence quickly, and we already started seeing some event which made some excitement in the early days, and also keep us going and for bigger detectors. And then a new series of workshops also started from KGF. It is called ICOBAN, International Colloquium for Barium Non-Conservation, and the first of the series held in Bombay in 1982. And all the pioneers all over the world who are working either on the theory or in the experimental side of proton decay came to this meeting actually. And in fact, if you see in this, I can point out each of them and who's who, and everybody was there actually. Paul Langekar, you can see here sitting in the young age in the front. So this was actually very, very exciting time for all of us to go through this experiment. But then soon we realized that we need a bigger detector and we need a much bigger site. So we dug out a bigger lab and started almost 400-ton detector there. And this came around 1983. We got the lab ready. And by that time, of course, my thesis had been submitted, but the lab was ready. And then we started putting new counters and make another stack there. This is actually something like 6 meter by 6 meter by 6 meter detector, and with 60 layer of proportional counter, all 6 meters high. And this also started operational by 1983 end. And a third detector using 5 centimeter by 5 centimeter we put in front of that big detector, and this was mostly later on used for monopole detection later. So you can see within a short span of time, a large number of proportional counters made all at KGF. By the way, we had during this time when the second detector was built, we were asked by Professor Menon that why not you go and make those counters at Bell? Why make at KGF? Because he was actually that time heading the Bell Labs also in administrative capacity, and so he was managing director of chairman cum managing director of Bharat Electronics Limited. So we, on using his influence, we went there, but we couldn't make anything there. We had to come back from there shortly. So we came back from there, and then but this detector is built, and then some of these beautiful thing you can see. This is a neutrino going through our detector, upward going neutrino, and you can see clearly how beautifully this can be. We have seen measure of them and we published them. On the right side, you see I am showing the muon curve, intensity curve as a function of zenith angle, and you can see there are clear two components. The lower angle up to 55 degrees is dominated by atmospheric muon, but then the second one is coming up after 55 degrees at that depth is dominated by the locally produced muon by the neutrinos. Okay, so there are no question there. So we are all doing that one, but it is on a much smaller scale at that time. And by that time, of course, ultimately in this experiment lasted up to 1992, and when we are told that the KGF gold mine will get closed, and this time it did get closed actually, and so we moved out, and these counters have moved to Uti, and where probably still they are using some of them now. Anyway, so this is a short history of what happens in KGF in those times, an exciting time, and but of course, and in between we are involved in other type of detector development at TIFR for D0 experiment, scintillator detector with fiber. For CMS experiment, Satya was talking about, we made this outer hadron calorimeter completely in India, and for that is also a scintillator and fiber-based detector. However, since I'm talking about the underground now, in the next some 5 minutes or so, let me just talk about a little bit about what is our going on now actually. And I would not say now because we are now old actually. Many of us have retired, and these ideas of this one from the time the KGF, and not only from the time KGF was closed down, even before that, when they're talking about KGF will close down, we are having meetings, and Kaushik organized one meeting, Ramnath Kaushik at Bangalore, and we had several other meetings. But ultimately, we are all talking about something has to be done. Rajaji was all the time was pushing that we have to do something in India. KGF is gone. Why not look at something? Finally, at the WAVE workshop that we held at IMSC Chennai, we decided that let's try. That decision was taken that okay, maybe we should try. But the real push for the detector didn't happen there. The real discussion was, as Rajaji always put, it happens in one of my colleagues' apartment at Calcutta, and with a when we are having some some drink there and a bottle of beer, and then decided, yes, okay, let's go ahead for the detector. And then as in the next couple of years, we were looking for a proper detectors, and then came out with this present idea of a iCal calorimeter. And it is not completely that we have been completely innovated this detector. It came from the earlier detector that Italians are proposing at the Italian tunnel called Monolith. But our ideas was much bigger and different. And then we built that detector, and we decided that we have to use a fast detector, and the RPCs came into our radar. And then started a long R&D phase of this resistive plate chamber detectors that has happened. I'm not going to do that at all. And a lot of exciting things have happened. From the scratch, we developed and built those RPCs. And at the time, they are not functioning at all. But slowly, they started functioning. We built from small, some 10 centimeter by 10 centimeter to 2 meter by 2 meter finally, which are final goal. And every time we are making those detectors, we are making sure that they are performing well to the atmospheric muon measurement in those detectors. So here you can see fast stack in the top, the 30 centimeter by 30 centimeter RPCs, the middle one by meter, and in the bottom, 2 meter by 2 meter stack. This built up slowly, and now I'm not going to their details about their efficiency. We measure their fast timing has been proved that it is sub-nanosecond timing it can provide. Those are done very early. And with that confidence, we made the proposal that we can build the main detectors, and which was, as you know, was approved in 2015 already. And these are some of the tracks. Beyond tracks we have seen. We have developed the gas research. Everything that is required is slowly indigenously being built. And by that time, BRC also came into our, helping us in a much bigger way. The whole engineering team from BRC was building many of these things that we needed for developing these. We are also going to the industry because we realized that we cannot make those RPCs ourselves, and went to the Pune and developed a technique how to make these RPCs automatically in a assembly line scenario, and establish everything, and finally gave that technology to both Asai Glass in Mumbai, and as well as to the Sangobian in Chennai, and they built some of them. Their magnet design was entirely done at BRC, lab, and finally it was designed. And then, as you know, the trigger, how it will be. Sudeshna's thesis was actually this is a student thesis. How we'll be developing our trigger scheme, and this idea have been implemented later by TIFR BRC team at the mini iCal that is running at Madurai. So in this process, we have slowly and developed the technology that is needed, and this is how an experimental high energy mega science project should run. And in the process, you go to the final goal, but in the process, you develop all the technology. Students get excited and so on, and you will build. I mean, this is I am not going to give because there are many experts now. They will be probably have already given you talk on the instrumentation, and so that is not my purpose here. I'm just showing you how in different scale, in different areas, people have come together and joined hands and built this one unique experiment that is INO. So finally, you have seen the mini iCal. They have built it. This is some of those pictures there, and it is running at Madurai beautifully, and all the components are working. And now they are going to ultimately soon the prototype iCal will be built, with a much bigger scale, around 400 RPCs will be used. And if we get not me, the people who are there, when they get the permission from the or the activists stop their activism, probably will build INO in near future to do its job. So this is some of these muon tracks in the RPCs that we have seen. So finally, this transparency, the old transparency, why I am going to repeat it again and again like a broken record, that why India should be interested in neutron interaction. Of course, we are excited to do a phone tracking experiment. And Actually, when we made this proposal that we will do the mass hierarchy, that time nobody was in the picture. Even now, mass hierarchy, if we had this experiment, we are the only player doing that. China will be coming, but China's experiment is very, very difficult. And people have said that when I can give you one lecture on that, why it is difficult, that experiment. So the real experiment will come from Dune and Hyper K, which is much later, will come in the 30s, actually. So there are still, importance of that one. But even if somebody else find it, before us by different technique, and doing it from a different technique, using this art matter effect and so on, is really unique. So there is exciting. And not only that, you will do many other physics. I mean, there are people here who will give you talk what else can be done using such a detector in India. But for me, it is actually the experiment that the young people telling that we can build it, we can also build an experiment which is world class, is the important thing. So in the process, we will develop cutting edge technology and a massive 50 kiloton magnet, the state of the art electronics, the online monitoring, data acquisition system. Science students across the country will have the opportunity to participate in building each of these components from scratch. Many are already doing it. All the INO students, the engineers, they are doing it. It will create an ambience of doing things with our own hands, a culture that is lacking in India. Thank you all.
Thank you very much, Professor Mondal, for your very, I would say, characteristic trademark talk on taking us almost, almost 100 years of science, starting with cosmic rays, starting with D.M. Bose's work, but taking us through various, I think, pioneering experiments, I must say, that you and your professors and seniors started and doing in KGF, and which has also led to many future mega science projects, which are now, we call them, but the confidence that one has built in terms of the solid physics that went into these experiments, but more importantly, you stressed again and again of training and building people and building the very large area, large size detectors and making them work indigenously. I think that is something which I think you and your generation of people have, I think, helped the high energy nuclear physics and community in this country, and for which I hope there will be continued efforts and progress in this. And as you nicely summarized at the end, I hope the hurdles for the big project that we are all looking forward, the INO project, will come through, and many, younger students today, and maybe some of them are just young scientists today, they all also have an upper hand in, in doing things which are typically done only abroad so far, but we could also do indigenously by our own country and by our own hands. So it's very inspiring and, of course, highly informational talk. With that, I would now request if anybody has want to ask you some questions, both on the Zoom platform as well as YouTube. Please raise your hand. I do see a couple of them on the Zoom here, but I will ask them to hold on for a second, and I'll go to YouTube to take some questions. As Prof. Mondal, these talks are also attended by non-specialists, so there will be also kind of wide range of questions. One of them are, what are the benefits of detecting neutrinos, and what information we can extract from them after detection?
So I will talk about broadly about the major result that was we are still waiting for in the neutrino field. For example, we know that the neutrino has masses, and there are three neutrinos and three massive neutrinos, but we don't yet know that what is the ordering of those masses. That means which one is the lightest of the three and which one is the heaviest. And this is the question that is called neutrino hierarchy problem. And this neutrino hierarchy problem is one of the most important questions that we are looking for an answer. And this is one of the the question we still have to find out. Then another important factor of neutrinos that we want to know is whether they are violating this matter antimatter symmetry. Okay, that means what you call in our technical language is CP violation. Okay, charge parity violation. And this charge parity violation, apart from just the science of it, it is very important for us, because probably if we can find the charge parity violation in the neutrino sector, it will give us answer to why in our universe we have only matter and no antimatter. Okay, so this is some of the question, but there are many other questions. I mean, neutrinos can be used for it. For example, Earth tomography. Okay, using neutrinos. I mean, these are all much later, but some of the important questions. And then there is another question. For example, I'm only talking about this ICAL experiment, but there are other experiments in the neutrino physics. For example, neutrinos, there can be either a Dirac particle or a Majorana particle. Okay, a Majorana particle, neutrino can be its own antiparticle. Okay, and whereas Dirac particle, then particle antiparticle are different. So whether neutrinos are its own antiparticle, we don't know. The detector that we discussed here will not answer that question. But in the same lab, there was a proposal for setting up a what we call the neutrinoless double beta experiment, which will answer that question. So there are many such questions that need to be answered in the neutrino sector. What is the absolute mass of the neutrino? We don't know that also. So there are many questions, and different labs all around, different experiments all around the world are trying to address each of these questions, with their own expertise and with their type of detectors.
The same participants is Abhinav Chaudhary. So this is a more direct question. Which flavor of neutrinos were detected at Kolar goldfields?
The muon neutrinos.
So again, there are some more questions on YouTube, but we'll come back after taking a couple of questions on Zoom. There's a question from Hariom. Can you please ask your question, Hariom?
Yeah, hello, sir. Sir, my question is, how many number of neutrino events detected in this Kolar goldfield? And what was the, like in case of iron, we are using this 50 kiloton iron to get 10,000 events in 10 years, right?
Okay.
So what is that?
Good. Okay. So so let me just tell you the way we are detecting neutrinos at Kolar goldfield in 1960s and at INO is little different. In the Kolar goldfield, we are asking the neutrinos to interact in the rock surrounding the detector, and then it will produce a muon neutrino will come, will produce a muon, and will detect that muon. So that is how we are detecting there. We have this not me, actually my seniors have seen roughly around 220 events. Out of them, and around 25, if I'm correct, is near horizontal events. So they're definitely neutrino events. Okay, and those events are those that I have plotted in the sky plot also. And at KG, and the second question is how many events and why do we have to run for 10 years? Because neutrinos are hardly interact in matter, and in our experiment at ICAL, we'll roughly get 3 events a day. Okay, so now if you have to have a statistically significant number, you can come with those numbers that how many years you have to run and how many kiloton detector you need. So that 50 kiloton and 10 years is coming from that.
Okay, question from Kolahal. This is our own, of course, Kolahal Bhattacharya. Please ask your question, Kolahal.
Hello, sir. Good evening. So I have a question that you may know, like many of the international neutrino experiments these days, they are mostly shifted towards the cryogenic systems and say liquid argon based or liquid xenon based technologies. I mean, my question is that, I mean, the future of neutrino detection in India or the particle physics experimental research in India, the programs. So, should we be looking at something similar? Like, I mean, I understand that, I mean, in ICAL, we have this sampling calorimeter, magnetized calorimeter system. But, I mean, should we also not look into, I mean, similar technologies which will be detecting based on these liquid argon or liquid xenon technologies? That is my question.
Well, so actually, we have to start where our expertise lies at the beginning. And I agree with you. I mean, once we have developed technologies, then you can go in different direction. So right now, and the technology for liquid argon or liquid xenon doesn't exist actually, and it's not a great thing that we cannot do it. You can do it, but we have not spent our efforts or time of energy for that kind of detector, because when we thought about INO experiment and we wanted to have where our expertise lies. Secondly, we wanted to do something where others are not doing. Okay, and but your to answer your first question, I don't think this it is all liquid argon or liquid xenon. Yes, liquid argon, liquid xenon is used. The hypercommutative will be still water-based, which has been used for last
Yes,
35
yes.
years. For them, they have not changed their detector. There are liquid scintillators detectors are coming up, and new detectors are coming up. So neutrino field is wide open. Okay, you need different kinds of detector based upon what science you want to do. So you choose your detector and sign to match these two, and then you decide and go ahead. But for us to venture out in all directions with the limited expertise that we have, or limited, not expertise, I would say, limited number of trained manpower that we have, will be not proper actually to me. Then you will be lost. So you better go in one direction or 1 or 2 directions. For example, there is a double beta decay group is growing. There is a plan for some kind of dark matter experiment. So let's concentrate on those. In fact, if you are asking that, I certainly know that BRC group is trying to have liquid scintillators. I mean, at the moment they're using plastic scintillators for detecting neutrinos. That is not RPCs or anything, and they have much low energy threshold compared to us. So this, depending upon again what kind of science you want to do, you choose your detector.
Yeah, thanks.
Okay. Prof. Mondal, we still have quite a few more questions. But let us take one right away from Lakshmi.
I think this Kola, Lakshmi, they all know all the answers.
Yeah. Actually,
they're asking questions.
I should actually take some questions. They're waiting.
They will answer the question.
Lakshmi, can you? No, but Lakshmi was looking for your talk, by the way. She was asking about KGF experiment. So, Lakshmi, are you there? Okay, we will come back.
Lakshmi, please ask question. I just made a joke.
No, I'm sure she'll ask. There is a question from Rupesh. Rupesh, are you there on the RG? I think is you, right? So,
hello, sir.
Yeah, can you please ask yourself? Yeah.
Hello, sir. Good evening. I would like to tell you that thanks a lot for this fantastic talk. To be very honest, I do not understand many things because I'm not a physicist. I'm an engineer. So currently, I'm working for the ITER project and now located in Cadarache. So I follow most of the updates on the INO Facebook page. My question is more general regarding the project status. What is the status of the project now?
That probably at this moment, I'm not the person to answer that question. And there are more, is Satya or Govinda, one of them can answer the question.
Anyway, Professor Datar is there. If your successor,
Professor Datar also can hear.
INO project director. Professor Datar, are you there?
Might have left.
Okay. Currently, we are just to answer in a very couple of lines. As Professor Mondal mentioned, we have been right now still doing some small prototypes of exactly using the same technologies which are going to be used for INO project. We want to build a next bigger prototype called engineering module that is coming up in Madurai on surface, but once again is a bigger scale, but it's not quite like a neutrino experiment per se, because being on surface, it will only track cosmic particles. But what is important is to validate and vet the engineering technologies that are going to be playing role in the used in the ICAL experiment. The
Okay.
ICAL, of course, before that requires a site and underground cavern to be built. Unfortunately, and this is going to happen somewhere in West Bodhi Hills, which is a border between Tamil Nadu and Kerala. And right now we are stuck with certain approvals coming from, for example, one of the things that we are right now waiting is for the so-called wildlife permission that needs to come up still from both Kerala and Tamil Nadu governments independently. Then it will be also followed by what is called Pollution Control Board approval. We have gone through that, but there has been some, some revisions, or you can say, reapprovals what are required. And ultimately, we also have one case pending in a Madras High Court. Hopefully, once you have the uh, Pollution Control Board approval, I think the other thing should be able to kind of go off. So to summarize, I mean, we are not stuck due to any technologies or any other work, but at the moment we are stuck because there has been some delays in getting government approvals. As also Professor Mondal said, there has been some misunderstanding in the local public's mind about what neutrinos does to them, what the construction does to them, and so on. And we have been trying to engage with them and trying to make them understand this for a very long time. All of us spend considerable time in the public outreach. In fact, in a way, these efforts that we are doing online during the COVID situation is also where we can kind of, get such interactions taking place. So unfortunately, we are stuck at the moment until we receive the various government approvals for the construction of the lab at the project site.
Okay. Sir, can I ask one more question?
Yeah, okay.
What type of now I understand that you are going to have a bigger prototype, and how the industry involvement in the project, because now most of the international collaborations also, we have a lot of industry interactions, and Indian industries have been able to produce a fantastic job. So what kind of industry involvement are actually is going to get involved in the project? Of what scale, or what are the main technological challenges we will be facing in the actual project scale?
Yeah, Professor Mondal.
See, I think again, probably Satyanarayana is the right person to answer that question, but I'm just telling you that all areas. See, I have gone through actually this development, the INO part very quickly, simply because I am sure that you have heard from others like Satyanarayana and in this series about what is going on in detail. And I didn't actually. I wanted to take you to the past rather than on the present. But anyway, each of these areas, for example, I have already mentioned that take the resistive plate chamber idea. There are many things involved in that one. Graphite coating on the glass plates, which has to last for longer period because it has to be resistive. That's why it's called resistive plate chamber. Then the making of the glass enclosure. That is why the Sankovian and Asai float glass were involved, and there are others have to be involved. Automatization, whole electronics, all those things that we're talking about. They're making this gas recirculation system, and making, how do you place those RPCs inside, the container and so on, movement of those ones, the making the magnets, and it connected to all these other, instrumentation and so on. Everywhere we have to go to industry, and they're already there. I mean, some identified, some are not identified, but most of them we are talking. I think Satya may be telling you the large number. A large number of industries we are interacted over the many years, last 10, 15 years, and developed this technology, sometimes together with them. Sometimes we have given them the know-how, asked them to build in large scale and so on. So there are this, approach is already there, and there is a large industrial participation will be there to make this project. Without industrial participation, we will not go anywhere.
Thank you very much, sir.
Okay, yeah. Lakshmi, are you there now?
Hello, am I audible now?
Yes.
Sorry, my mic was muted. So,
Yeah,
sir,
please go
actually,
ahead.
this is related to a little bit physics, because when I was reading about some flux measurement, so the pre-Super Kamiokande era detectors apparently looked at the up versus down ratio. They were also measuring the flux of atmospheric neutrinos, and some of those experiments actually saw some kind of asymmetry, but they all said that okay, the error is too much, so we can't say about it. So KGF also did KGF also measure this?
No.
Hello?
So if you see, Lakshmi, if you see, the KGF was the pioneering experiment. So if you want to do that kind of details measurement, you have to have statistics. Okay. KGF is a small experiment. It is a kind of experiment to establish that atmospheric neutrinos are there and measure them. But KGF didn't have the statistics to do all the up-down asymmetry and so on.
Okay. Okay.
That
Thank you, sir.
that okay, Lakshmi?
Yes, sir. Yes.
Okay. Thank you very much. Okay, I want to get back to here. Maybe just one or two more questions. Very quick questions we'll take. Why are we using iron calorimeter for detecting neutrinos and not water like in Super K of Japan?
So I think I have already talked about that in answering some of the earlier question. Yes, you have to. I mean, if you do the iron water-based detector, why do you need another water-based detector? Because that is already there, and they're doing a great job. But you have to, when you do some sign, you have to do from different angle. You have to look into differently. For example, the iron detector has the advantage that you can magnetize it. Okay, so you can simultaneously look at mu plus and mu minus. Water Cherenkov, like Kamiokande, they doesn't have that. So they have no ability. They have, of course, they have statistically they will do because the neutrino cross section and anti-neutrino cross sections are different and their flux are different. So using that in statistical basis, they will be able to do, but they will not be able to say event by event whether it is a neutrino event or whether it is an anti-neutrino event. Whereas a detector like ours, because we are using iron, which will be magnetized, we have that ability. So that is the main reason why we are doing iron-based detector, because this is the way we can complement what, let's say, Super Kamiokande is doing or what Hyper Kamiokande will be doing. In fact, this is actually, at this scale, ours is the only magnetized detector that exists, that has been proposed. Everybody else has non-magnetized detector at this scale.
Hariom, I understand you have one more question. Can you ask very quickly?
Yes.
I think we'll close it after this. Yeah.
Yeah. Sir, my question is this number of events you told this to around 225 neutrino events, and that statistics is very less. And
Event.
second thing,
Total event. 225 is the total event that also consisting. Some of them are atmospheric muons.
So that statistics is very low.
Yes, so that is discovery experiment. See what happens, the W boson when discovered by CERN, they are only a handful of events. But if you go now, they are producing them in millions. So discovery is always, because this is in 1965. So they have a small detector and they did that experiment.
Okay, even though there are, I think, more questions, but we are already now crossed 2 hours almost. So on behalf of all of you, once again, I would like to thank Professor Mondal, in spite of his very busy schedule of various other assignments, even at this age. So he readily agreed, and I hope it was very useful to especially the younger members of this group. And so thank you very much, Professor Mondal. And once again, I would would like to say for the next week, again, we have 3 more interesting talks. Please come back on Monday. As I already mentioned, we have an interesting talk on the detector, which partly also today it came on and off about the dual phase xenon based time projection chamber, which is the workhorse nowadays of many neutrino and other experiments. And this is going to be given by Professor Matthew Zidagis from the State University of New York. So that is on Monday at 6 p.m. So please join. Until that time, please take care and stay safe. Thank you, Prof. Mondal. Good night.
Thank you all. Good night.
Thank you, sir.